discussion of impact of a jet. So in this section, we are discussing about a curved vein. So here the curved vein is unsymmetrical. That is, the inlet tip angle is theta and the outlet tip angle is phi. So the condition is that jet striking the moving curved vein tangentially at one end. So the jet is striking at one end and leaving at the other end, and the tip angles are different. So this is the case of unsymmetrical unsymmetrical so unsymmetrical curved vein. So in order to analyze the velocity or the analyze the movement of a jet in a curved vein where the water is falling at one end and leaving at the other end, we need to draw a velocity triangle. So velocity triangle, by drawing velocity triangle only we can analyze the various conditions of the movement of a jet and how it affect the movement of the vein. So the jet is striking this vein, and this vein is moving with a velocity u. Vein is moving with a velocity u, and the jet is striking the plate at velocity v. So at the inlet we can give it as 1. So inlet is 1 and the outlet is 2. So the parameters written at the inlet are given as v1. So we are giving a suffix v1. If we are considering relative velocity, then we are giving it as vr1. So at the inlet we are giving it as v1 vr1. If the inlet the velocity of the vein at the inlet will be u1. So at the outlet similarly, and the velocity of the jet will be v2, the relative velocity of the jet will be vr2, and the outlet the vein speed at the outlet will be u2. Like that we are denoting. Okay, let us look into the details of the inlet velocity triangle. So from this figure it is known that there is a nozzle. So this is a nozzle. So from this nozzle the jet of water is coming out, and this jet strikes the vein, but the vein is moving with a velocity. So water strikes the vein at a relative velocity only. Okay, water strikes the vein at a relative velocity. Since the vein is having velocity u1, and the absolute velocity, that is the velocity with which a jet leaving the nozzle, is absolute velocity. So the absolute velocity is v1. Absolute velocity is v1. Since the jet is striking a moving curved plate, and actual velocity with which a jet strikes the plate will be at a relative velocity only. So we are taking relative velocity term as that is vr1. So here the absolute velocity with which jet leaving the nozzle is v1, and the jet angle, the angle with which jet makes with the horizontal or in the x direction, is alpha. Alpha is the jet angle at inlet. Alpha is the jet angle at inlet. So absolute velocity with this jet moving is v1, and it makes an angle of alpha with the x direction or in the direction of motion of the vein. So next, since the blade or the vein is moving with a velocity u1, so the vein velocity is denoted at inlet as a horizontal line. So this distance A to C, this distance A is represented as U1, that is the velocity of vane at the inlet. Velocity of vane at, this is the velocity of the vane at inlet. So we are considering the absolute velocity with which jet issuing from the nozzle, and the vane has a velocity u1 at the inlet. So the relative velocity, so there will be a relative velocity with which the jet strikes the plate. That velocity is represented by the line BC. BC represents the relative velocity with which jet strikes the plate. So VR1 equal to relative velocity. Relative velocity. Relative velocity with which jet strikes the plate. So the three terms are absolute velocity and the velocity of the vane at inlet and relative velocity with which jet strikes the plate. So the other two terms are also shown here, that is Vf1 and Vw1. Vw1 and Vf1. So Vf1 means velocity of flow at inlet. Velocity of flow at inlet. Velocity of flow at inlet. And Vw1 equal to velocity of whirl or whirl velocity. WHIRL, whirl velocity, velocity of whirl. So Vw1 represents velocity of whirl. So what exactly is Vf1? Vf1 is the vertical component of V1. So Vf1 is actually a vertical component of V1. Vf1 is vertical component of V1 and Vw1 equal to horizontal component of V1. Horizontal component of V1. So these two terms Vf1 and Vw1 are the components of V1. If we draw V1 like this and it is making an angle alpha to the horizontal, so the x component of V1 will be Vw1 and the y component of V1 will be Vf1. Like that it is taking. So the x component is Vw1 and y component is Vf1. So all these constitutes the velocity triangle at inlet. The velocity triangle at inlet consists of the following components: V1, V U1, VR1, VF1 and VW1. So drawing this velocity diagram is important for analyzing the vane, moving curved vane when the jet is striking at one side. So this is very important portion and you must study this inlet velocity triangle thoroughly. So the inlet velocity triangle consists of V1. V1 is represented by AB, the line AB, and U1 is the non-component, that is velocity of the vane, that represented by U1. So represented by the term AC or the line AC, and CB represents VR1. CB represents VR1 and AD represents Vw1, which is the horizontal component of absolute velocity, and BD represents Vf1, which is the vertical component of the absolute velocity V1. So these terms includes a velocity triangle, and you have to study this velocity triangle. So it is very important in this portion. So velocity triangle at inlet. So that is all for the velocity triangle at the inlet. Now let us look into the details of the velocity triangle at the outlet. So this figure represents a velocity triangle at the outlet. We know that the absolute velocity, that is actual velocity of the jet at inlet, is V1. Here we are taking it as V2, that is actual velocity of the jet at outlet, or absolute velocity of jet at outlet is VW2, and it is making an angle beta. So beta is the angle of absolute velocity angle at outlet, absolute velocity angle at outlet. Inlet, we know that we take it as alpha, angle alpha is the velocity, absolute velocity angle at the inlet. So here it is V2. So next, the relative velocity with which the jet leaves the plate. Relative velocity with which jet leaves the plate is VR2, and it leaves the plate at the angle of outlet angle of the blade. It is the outlet angle of the blade, which is phi. So it makes an angle phi. So VR2 is the relative velocity term. Relative velocity of jet leaving the plate. Relative velocity with which jet leaves the plate is V2, and it makes an angle phi. And U2 represents the velocity of a vane at outlet. U2 represents velocity of vane at outlet. But in this case only, for this case only, actually the velocity at inlet is equal to velocity at outlet, which is equal to U. That is the actual velocity with which the blade moving in x direction. So that is known as U. So in this case only, and the velocity of vane at inlet and velocity of vane at outlet will be equal. But for other problems, we need to take it separately. So it is represented as U1 and U2. So U2 is the velocity of vane at the outlet. So we know that VW2 is the velocity of whirl velocity at outlet, and Vf1, here we are taking it as Vf2 is equal to velocity of flow at outlet. So in the previous, similar to the previous case, here Vf2 represents the vertical component of absolute velocity V2, and Vw2 is the horizontal component of absolute velocity V2. So these are the two terms. Vf2 equals vertical component of absolute velocity V2, and W2 is the horizontal component of V2, absolute velocity V2. So the in the figure, B dash C dash represents VR2. B dash C dash represents VR2, and C dash A dash represents U2, and B dash D dash represents VF2, and B dash A dash represents absolute velocity V2, and A dash D dash represents velocity of outlet. So all these terms are included in the velocity triangle at outlet. So this is also important. So you must study the inlet and velocity triangle thoroughly so that we can analyze the various factors of the blade velocity, and we need to find the work done and the power developed by the vanes. So in order to analyze the vane, we need to understand how the velocity triangle to be drawn. So this is important. In this figure, it represents the outlet velocity triangles only. And in the previous figure, we had discussed about the inlet velocity triangle. So now we can look into the velocity triangle at the inlet and outlet. So this is the figure which shows the velocity triangle at inlet and outlet. So at the inlet, the velocity triangle is represented by A, D, B, and at the outlet, it is represented as B dash, C dash, D dash. So the various terms included in this diagram are absolute velocity term at inlet, V1 at inlet, and at the outlet it is V2. The jet makes an angle of alpha at inlet, and at the outlet it is beta, and the velocity of the vane at inlet is u2, and the velocity of vane at outlet is u2. Sorry, the inlet is u1 and at the outlet is u2. So velocity of the whirl at inlet is, that is the x component of v1 is vw1. At the outlet, the x component of v2 is vw2, and the y component of v1 at inlet is vf1, and the y component of v2, that is y component of absolute velocity at outlet, is vf2. Relative velocity at inlet is vr1, and relative velocity at outlet is vr2, and the relative velocity makes an angle of theta at the inlet, that is the blade angle at the inlet, theta at inlet, and blade angle at outlet phi. So relative velocity at outlet makes an angle of phi at outlet. So these angles are taken in the direction of motion of, with respect to the direction of motion of a wave. So this is the velocity triangles of a curved vane. So in this slide, the various terms are described: V1 and V2, absolute velocity of jet at inlet and outlet respectively; U1 and U2, peripheral velocities of the vane at inlet and outlet respectively; VR1 and VR2, relative velocity at inlet and outlet respectively. Vf1 and Vf2 velocities of flow at inlet and outlet respectively. Vw1, Vw2 velocity of whirl at inlet and outlet respectively. So phi and theta and phi represent tip angles at the inlet and outlet. Alpha and beta are the angles which the absolute velocities makes at inlet and outlet. So the absolute velocity, the angle with which absolute velocity makes in the direction of a jet is alpha and beta. So important thing you have to notice is that all angles are measured in the direction of motion of a vane. Velocity of whirl is, so this is very important. Velocity of whirl is the component of absolute velocity in the direction of motion. In the direction of motion means we can take it as horizontal direction. So the component of absolute velocity in the direction of motion, and velocity of flow is the component of absolute velocity normal to the direction of motion. So these three things uh, you must be careful while drawing the velocity and diagram. So next we can derive the equation or expression for force exerted in the direction of motion. If the vane is smooth, that is having velocity in the direction of motion at inlet and outlet equal. So vane is smooth and the velocity at inlet and outlet are equal. So for this particular case, and the velocity of vane at inlet and outlet is equal and is equal to u. And also, since the vane is smooth, the relative velocity at inlet and outlet is same. Relative velocity is also the term relative velocity or the magnitude of relative velocity at inlet and outlet is also same. So mass of water striking the vane per second. As we know that the mass of water striking the vane per second is rho A. In the earlier case, we take it as V minus U. That is, this V minus U represents a velocity, relative velocity VR. So, the mass of water striking per second will be represented by rho A VR1. So at a relative velocity, it is striking the vane at inlet. So the mass of water striking per second equals rho A VR1. A is the area of the jet of water. So force exerted in the direction of motion will be F of x. F of x is the force exerted in the direction of motion. So mass of water striking the vane per second. So mass of water striking the vane per second is VR1. Initial velocity with which jet strikes in the direction of motion. So next we need to consider the initial velocity with which jet strikes in the direction of motion and final velocity. So mass of water striking in the vane per second will be rho AVR1. So initial velocity with which it just strikes in the direction of motion. We need to take the striking of jet in the direction of motion. So we took it as VR1 cos theta. So the jet is striking the vane at a relative velocity. So jet is striking the vane at a relative velocity. So in order to consider the relative velocity in the direction of motion of the jet, so we have to take the x component of relative velocity, that is VR1 cos theta x component. So this is VR1 cos theta. So x component of relative velocity, so VR1 cos theta. Similarly, the relative velocity with which jet leaves the plate is VR2. So in the direction of motion of the jet, we need to take the component of VR2 in the direction of motion of the jet. So VR2, we need to take VR2 cos phi. So the jet is leaving in the opposite direction. We need to take minus VR2 cos phi. Since the jet leaves the plate in the opposite direction, we need to consider a minus sign or negative sign there. So we minus VR2 cos phi. So we know that VR1 cos phi, VR1 cos theta, VR1 cos theta is CD. So CD represents VR1 cos theta. So how will you take VR1 cos theta? VR1 cos theta is equal to VW1. VW1, that is AD minus AC gives CD. So AD minus AC gives CD. So AD is VW1 minus AC is U1. So VR1 cos theta is equal to VW1 minus U1. So VR1 cos theta, we take it as VW1 minus U1. For VR2 cos phi, so the x component of VR2 cos phi is equal to, actually it is C dash D dash. So C dash D dash is equal to C dash A dash plus A dash D dash. So it is U2. C dash A dash is equal to U2 plus VW2. So VR2 cos phi is equal to U2 minus VW2. U2 plus VW2, sorry. So VR2 cos phi is equal to U2 plus VW2. U2 plus VW2. Okay, substituting in this equation, so the term will become rho A VR1 VW1 minus U1 minus of, there will be a negative sign here, so the minus of U2 plus VW2. So rho A VR1 VW1 minus U1. So here plus U2 plus VW2. So we know that U1 is equal to U2. So these two terms cancels out, and the force exerted by the jet will be rho A VR1 VW1 plus VW2. So f of x is equal to rho A VR1 into VW1 plus VW2. So this equation is true only if beta is acute angle. That is, beta is less than 90 degree. So this equation is true only if beta is less than 90 degree. If it is greater than 90 degree, then if it is equal to 90 degree, not greater than, if it is equal to 90 degree, then VW2 term will be 0. So if here the beta value, if it is less than 90 degree, VW2 term will be here. But if we take it as beta is equal to 90 degree, so what will happen? This A dash B dash A dash D dash will be eliminated. It becomes 0. That is VW2 is equal to 0 if beta is equal to 90 degree. So VW2 term becomes 0. Therefore, the VW2 term will be eliminated from this equation. So rho A VR1 V into VW1. If beta is obtuse angle means beta is greater than 90 degree. If beta is greater than 90 degree, then diagram will be like this only. So the beta term will be greater than 90 degree. So at that time what will happen? The VW2 term will be positive. So it is in the same direction. Okay. So that is why here they will we no f of x will be rho a vr1 vw1 minus vw2. If beta is greater than 90 degree, that is obtuse angle, what will happen here? The negative sign will be eliminated at that time. So vw1 minus vw2, like that it will come if it is obtuse angle. Okay. So generally, so the two terms are there. One is positive and another one is negative. So we can generally it is written as f of x is equal to rho a vr1 into vw1 plus or minus vw2. So this is the force exerted by the jet in the direction of vane. Okay. So next, work done per second. Work done per second is equal to force exerted in the direction of jet into u. F of x into u. F of x into u. So rho a vr1 into vw1 plus or minus vw2 into u. Work done per second per unit weight of fluid striking. Per unit weight of fluid striking means dividing it with rho a VR1 is the mass m into g, unit weight m into g. So m into g. So work done per second per unit weight of fluid striking is equal to rho a VR1 into VW1 plus or minus VW2 into u divided by weight of fluid. Weight of fluid is rho a VR1 into g. So the final equation becomes 1 by g VW1 plus or minus VW2 into U. So this is the work done per second per unit weight of fluid striking. So this is the case of a jet striking a moving curved vane at one end and leaving at the other end.